Hi everyone, today we are going to be talking about Gauss's law. So let's get started with the idea of electric flux. Now, flux describes how much of something goes through a given area and is therefore the dot product of a vector field. So we want to specifically look at electric flux through an area, and it is proportional to the total number of electric field lines crossing the area. So we can say the electric flux, this symbol here, this is a capital phi or phi, however you want to say it, is equal to the electric field perpendicular to the area, or equal to E times the area times cosine of theta. Okay. We also describe this as the dot product. So this is also called the dot product between these two objects. Okay. So again, we're looking at electric flux through an electric field. So we take some area here and we see how much electric field is passing through this area. Okay, so we can also look at this in another diagram here. Perpendicular to the area, we will take that angle. So the angle between E, our electric field, and whatever is perpendicular to our area, and this will be our angle. So this is how we describe E perpendicular, okay, our perpendicular electric field and our area as well, okay. So, whoops. So we have the electric flux through an open surface. It gives us quite a simple equation here, but I have it better described here through a closed surface. So we can first talk about through a closed surface. Gauss's law is related to electric flux through an area. And so we want to know how to describe our electric flux given a closed surface area. Okay, so we have our flux, our electric flux, is approximately equal to the summation of the electric field, E, dotted into our change in area. Okay, or we can write this as an integral, and this is actually called a closed surface integral right here. So the integral with the circle in it, this is a closed surface integral, and we will take that into E, or electric field, dotted into dA. Okay. Again, our angle is between E and the line perpendicular to the area. Okay, where our area is on the surface. So think of it, you can kind of compare it to like forces. When we looked at forces way back when, it's like the normal to the surface. Okay, it's perpendicular to the surface area. Okay. So this is the electric flux through a closed surface. So compare that with our electric flux through an open surface. So we just don't have that closed surface, integral. All right. So we can look at different objects now. We can look at the electric flux over a spherical surface. This is going to be the most, probably the easiest, simplest. Okay, so let's first recall that our electric field due to a point charge, E, is equal to 1 over 4 pi epsilon naught times Q over R squared, and it's in the direction R hat, or the radial direction. Okay. We can use this electric field to find the flux through the spherical surface of radius r. So we will take this and dot it into the like normal to the surface, wherever that is. And we can simplify this. Our normal to this surface is going to be in the r hat direction. We can look at this sphere over here as an example. Again, we have our point charge and our electric field coming out of it. And to the surface, we will have a radial direction, again, just like our electric field, so that is R, or R hat, I should say. So if we plug in our E, which is 1 over 4 pi epsilon naught Q over R squared, R being our radius of this sphere, this is capital R here, and then we have R hat dotted into R, times dA, our change in area, okay, or our derivative of area. This R dotted into R hat, that will turn into 1, okay, because they're in the same direction. R hat dot R hat is equal to 1. So that's how it goes away over here, and we get all of the same constants out front, okay? So if we wanted to take the integral of this to find our net flux over the surface of this sphere, all of this, like I said, they were constants, 1 over 4 pi epsilon naught, Q over R squared, nothing is changing. And so then we just have our enclosed surface integral, dA, okay? Now, this, of course, is going to stay the same, but when we take our integral here, our surface integral, with our area, this is going to give us the area of a sphere. Okay, so that is 4 pi r squared, the area of a sphere. So when we simplify this, we end up with the net flux over the surface of the sphere is equal to Q over epsilon naught. So this is our net flux over a spherical surface. Okay. All right, so let's go ahead now and give Gauss's law a technical term, or a technical definition, sorry. So the flux of an electric field E through any closed surface, or a Gaussian surface, is equal to the net charge enclosed divided by the permittivity of free space. So this is what we just used. We used an example of the spherical surface, and we found this exactly, okay? So our flux is equal to our Q enclosed, or our net charge that's enclosed in the surface, divided by our permittivity of free space, which is a constant, okay? And note that this holds for charges of either sign, whether it's positive or negative, okay? All right. One thing about Gaussian surfaces is that they don't need to correspond to a real or physical object, and usually doesn't, but it's a mathematical construct that can be any shape, provided that it's enclosed. So we tend to choose shapes that are highly symmetrical, say like a cylinder or a sphere, to be able to integrate over it. So we want to be able to integrate easily. All right, so let's go ahead and look at applying Gauss's law. So we can find a Gaussian surface over which the electric field has a constant magnitude, okay? And if E is parallel to N everywhere on the surface, then A dot N hat is equal to E, the magnitude of the electric field. If E is anti-parallel to N hat everywhere on the surface, then E dot N hat is equal to negative E. So this is what I was talking about, where we had the spherical surface and E was in the radial direction, and so was N hat. N hat was also in the radial direction, R hat. So if we have these two in the same direction, like this guy here, then we have just the magnitude of E, okay? If they're complete opposite, so if they're anti-parallel, then we get out a negative here, okay? So, like in this example here, so we have A1, area 1 and area 2, where we have a positive charge and a negative charge, and we have our electric field lines, okay, going from the positive to the negative. So the direction of the electric field for A1, okay, is in the same direction. But in A2, the electric field is now coming in, and our area is always going in the direction perpendicular to our surface. So it is going in the opposite direction. Okay, so let me show you real quick. Let me get a black pen. So our area would be in, say, this direction. It should not be curved. So it is opposite of our electric field lines. Okay, so this will give us that negative value. Okay, so we can take Gauss's law and we can simplify it a little bit. In this case, we can have our phi, our flux, our electric flux, is equal to the surface, enclosed surface integral of E dot N dA. So we're taking it over the area. And that will simplify down to E times A. And we still say that's equal to the charge enclosed over epsilon naught. Okay, so this is what can also come out of Gauss's law. So, say we're looking at this oddly shaped, enclosure, Gaussian surface. Our overall flux could be Q enclosed over epsilon naught, or negative 2Q plus Q over epsilon naught, which would give us negative Q over epsilon naught. Agreed? Okay, remember our Q enclosed is going to be the total charges that are enclosed in this surface. Okay? All right, so let's move on to a problem-solving strategy. So there are about 5 steps, give or take, and the first thing is to identify spatial symmetry of the charge distribution. So for example, what we will see, an isolated point charge has spherical symmetry. An infinite line of charge would have cylindrical symmetry, so we can kind of treat it like a rod. And then charges that are uniformly spread over a large flat surface has planar symmetry. So we will choose a Gaussian surface with the same symmetry as the charge distribution and identify its consequences. We'll evaluate the integral over the Gaussian surface and therefore calculate the flux through the surface, and then determine the amount of charge enclosed by the Gaussian surface. Then we can evaluate the electric field of the charge distribution using both 3 and 4. Steps 3 and 4, I should say. Okay, so we will go over some examples of this in class, and we'll also have that in our problem-solving assignments. Okay, so let's talk about these different types of symmetry. So there's 3. We've got spherical symmetry, which is going to be a charge distribution where the density of charge depends only on the distance from a point in space and not on the direction. So basically, if you rotate the system, it doesn't look any different. So we have some examples down here. A is spherically symmetric. Our charge density rho, or rho naught, is the same throughout the entire body. Okay. With B, we are not spherically symmetric because we have a charge density on the top half hemisphere, and then on the bottom hemisphere we have a different charge distribution, rho 2. So rho 1 and rho 2 are not equal here. Okay. Then we have another one that's spherically symmetric, because as we go out, we do have different charge distributions, but it's only in the distance from the center. So say from, come on, whoop, the center here, okay? So as we go out, the charge distribution does change, but it's not based on, half and half. This is cut exactly in half, and then we have a solid um, hemisphere of a certain charge distribution. Okay? All right. So let's look at spherical symmetry and Gauss's law. So we start with the same idea. We have phi is equal to this surface integral of E, our electric charge at some point, dotted into N. And we will end up with our electric field at some point is equal, times 4 pi r squared, where 4 pi r squared is our area of the sphere. Okay, so we can now set that equal to Q enclosed over epsilon naught and solve for our electric field. So our electric field then is 1 over 4 pi epsilon naught times Q enclosed divided by r squared. So this is what we can boil down to with our spherical symmetry. So this is our electric field of a sphere. Okay. Now for an enclosed charge for spherical symmetry, because we don't have that, we have two different cases. So our Q enclosed could be our total charge. That is if R is greater than R. Okay, what does that mean? So basically, which I should have drawn this, I don't know what I was thinking, but if we have a circle and another circle on the inside, so our R, capital R, would be like so for this case, and lowercase r would be like so. So lowercase r is going to be of your Gaussian surface, and capital R is going to be of the physical surface that we're looking at, so our charge or something, okay? So what we're integrating over, okay? So we have Q total would be if we are looking at our entire system, okay? But if we have the opposite, let me draw this, whoops, sorry. Q within R is less than capital R. So here we'd have a capital R is the larger surface, and the lowercase r is the smaller surface, okay? So our Q enclosed would be within this surface. If we're kind of taking like a chunk out of whatever our sphere is, our surface that we're interested in, our charge that we're interested in, okay? So we have the same exact equations that we just got, but we now just have put in Q total, or Q within the R is less than capital R. Okay, so again, we will kind of look at this a little bit more, and I will insert a couple better images for this guy. All right, next we have cylindrical symmetry. Now this is going to be a charge distribution where the charge density depends on the distance r from the axis of the cylinder and must not vary along the axis or within the direction about the axis. So what does it mean by the axis of the cylinder? It means like along here. Oops. Okay, so it will depend on the radius from that point. like so. This would be your R here, okay? So let's look at some examples. We have cylindrically symmetric, which we have a charge distribution that is the same throughout. These next two are not cylindrically symmetric because they have that same sort of thing when we were looking at the spherical symmetry, where we had two different areas that were not the same charge distribution. So this one, we have the top half is rho 1, the bottom is rho 2, and those are not equal, and they don't vary along the radial axis here. Okay, they're varying along, say, the z-axis here. Let's pretend that's the z-axis. So it's varying along that z-axis. Okay, so let's see. This one as well is varying along a different axis. So let's see, the direction about the axis. So it is, again, not varying cylindrically, I guess we could say. So this one here, D, is cylindrically symmetric because it does vary like so, okay? But this one is not symmetrically varying. Okay, I hope that makes sense. So again, we can look at Gauss's law with this. We're going to take our surface integral, and the integral of our surface area is going to give us our area of a cylinder, so 2 pi r times the length of that cylinder. So one thing we should note is that the flux through the end caps of the cylinder is 0 because our electric field is not flowing in that direction. So our electric field dotted in into n hat is 0 there, okay? So when we take our surface integral, we end up with 2 pi r times the length of our cylinder times E, our electric field. Okay, and again, setting this equal to Gauss's law, and remembering what Q enclosed is for a cylinder. So Q enclosed for a cylinder is going to be lambda enclosed times L. So this will be, oh shoot, if I remember correctly, but it is our charge distribution, I believe, for a line. Okay, so this is going to be our charge enclosed. And so we can rearrange our equations and plug some stuff in, and we end up with this electric field, okay, which varies radially. So lambda enclosed over 2 pi epsilon naught times r. Okay. All right, so what is going to be our Q enclosed for this guy? It's going to be very similar, but now we have a couple of images, which is great. We have our cylindrical surface, which is the, I don't know, peachy part, the pink or peach colored object here. And so we're going to place a Gaussian surface along some line of this charge distribution. And we have an electric field that's coming out of it, and let's see, our R hat is in the same direction here, and this is for our total charge if R is greater than R, greater than or equal to, R being the radius of the Gaussian surface, and capital R is of the actual object, the physical object. Okay, so again, just pay attention to what the enclosed means. So that is our first case here, where R is greater than or equal to capital R. If we have R is less than capital R, so our capital R is larger here, okay, it goes out to here, Then we will need to say, okay, our Q enclosed is only the charge within this bit. Okay, within that Gaussian surface. All right, let's look at our last one, which is planar symmetry. So this is, again, charges that are uniformly spread over a large flat surface, and uniform charges in the XY plane typically. So we will have some electric field at some point is equal to E, our electric field, in regards to Z, in the Z hat direction. Okay. So this would be like our XY plane, and our Z direction would go straight up, like so. Okay, whoops. So, again, looking at planar symmetry and Gauss's law now, our magnitude at um, different sides, let's see this. Okay, so we have our planar surface, okay, and then we're going to choose something like a box, and we can find our electric flux through this box. Okay, this is going to be our Gaussian surface here. Okay, so actually, let's see, planar symmetry. Okay, so we're going to take this box here, and we have one side over here and then another side over here, side 1 and side 2, and you can see that our electric field is in the Z hat direction. Okay, we have our Z hat direction, and our electric field on the other side, so one of the, how do I say that? The XZ plane, one of the sides on the XZ plane, we have the area is perpendicular to that. Of course, that's what we've been doing this whole time. The area is perpendicular to our Gaussian surface, okay, or our surface, and the electric field dotted into our area here is going to be 0, okay? So all other sides that are not along the Z axis is going to have a 0 flux, okay? So that's kind of looking at this real quick, is our E and our delta A on the sides of these boxes, or this box, is going to give a 0 flux, and so our only flux that we get is from the top, side 1, and the bottom, side 2. Along our z-axis is where our electric field is. Okay, so we find the flux of electric field through the box, where the zeros are for the flux on the other sides of the box. So like I was just saying, our flux is going to be our surface integral EP dot n hat dA. So we get back EP, so our electric field at some point times the area, plus the electric field at some point times the area, and so we get 2 EPA. Okay, and so we also need to look at our Q enclosed, which is going to be our density, epsilon naught, times our area. Okay, and again, we'll use our Gauss's law to plug that stuff in, and we will obtain our electric field, EP, is equal to sigma naught over 2 epsilon naught in the n hat direction. And the n hat direction depends on if we are above or below the plane. So above the plane, we are looking at n hat is equal to positive z hat. And below the plane, n hat is equal to negative z hat. Okay, so it just depends on where we are interested. Okay. All right, we are now in our last section here, looking at the electric field inside a conductor. So remember how conductors are, they can be induced of a charge, right? So, or at least the distribution within the conductor. So for example, we have this conductor here, and we placed a charge close to it, a positive charge. We induced a negative charge on the near this A here, and on the other side we have another set of charges that were induced positive. Okay, so we have a negative sigma A on the A side and a positive sigma B on the B side. Okay, so if an electric field is present inside a conductor, it exerts a force on the free electrons, which are electrons in the material that are not bound to an atom. We talked about this last time, just a bit about free electrons. So these electrons do accelerate, and when electrostatic equilibrium is reached, the charge is distributed in a way that the electric field inside the conductor vanishes. Okay, so in this case, the electric field inside the conductor will vanish. So the net field inside the conductor is different than the field outside the conductor or on the surface of the conductor. Okay, so when we're looking at this situation where we induce some sort of charge distribution that's not zero, or we're separating these charges, the minuses and the pluses, okay? We have this redistribution of charges, and so our electric field at some point inside the conductor, okay, so this is inside the conductor, will be our net electric fields that are acting on this. So we've got EQ, EB, and EA, and they will all sum to equal 0. Okay, so because we have a Q enclosed that is equal to 0, our overall charge of the conductor is 0. This also means that our electric field, our net electric field is 0 at every point inside of a conductor. Okay, so again, electric field is equal to 0 at points inside a conductor. That's important to remember. Okay, so what about on a conductor? So I said that it's different. So then what is it? So because E is 0 everywhere inside of a conductor, we can give this equation for Gauss's law, where flux should equal 0. So let's see, from Gauss's law, there's no net charge inside the Gaussian surface, but the Gaussian surface lies just below the actual surface of the conductor. There is no net charge inside the conductor, so any excess charge must lie on its surface. So this tells us that there must be something going on the surface. So if this is a conductor, this entire thing, our Gaussian surface lies just beneath the actual surface, and all of the electric field is 0 inside, but outside there is still something. So for example, we have a conductor and a rod that is going to induce our charge distribution here. We have negatives around this rod that's positively charged. When it touches, then we have a surface charge of positives. So we need to figure out what is that electric field. So the electric field at the surface of a conductor then is going to be E is equal to sigma over epsilon naught. Okay, so at any point just above the surface of a conductor, the surface charge density sigma and the magnitude of the electric field are related by this here, okay? And from Gauss's law, this is how we get there. E times our area, our change in area, is equal to sigma change in area over epsilon naught, or E is equal to sigma over epsilon naught, okay? So this is like our conductor here, our surface of a conductor. We took a small cylinder as our Gaussian surface. Our electric field on the surface is pointing outward, okay, perpendicular to our area, and actually parallel to our area, I'm sorry, parallel to our area. We have some sigma, our charge distribution, and we also need to note that our electric field inside the conductor is 0. Okay, so again, in a conductor or on a conductor, our electric field inside is 0. Our electric field on the outside or our surface is sigma over epsilon naught. Okay, so our surface charge density divided by permittivity of free space. Okay. Alrighty, that is all I have for you guys. So we will again look at some examples during class, including our problem solving session. So if you have any questions overall, please let me know, and I will see you soon.